Hi everyone, I am Nasikun and today I'm excited to share our recent project on locally supported tangential vector and tensor field in this online Eurographics 2020. The idea of using some notion of tangential fields to encode directional information on the geometry is prominent in computer graphics. Some examples are tangential fields are used for BRDF editing. Rotationally symmetric fields guide the synthesis of artistic line drawings. Texture and stripes pattern on the surface align to the tangential fields on surfaces. The problem that we are addressing is that, at the one hand, editing tools require interactive responses. On the other hand, many triangles are needed to accurately represent complex geometry. Therefore, for vector field editing, we need to solve large-scale optimization problems. Our observation is that we need many triangles to be able to accurately represent a shape. And now, since the vectors are associated to the triangles, edges or vertices of the mesh, the degrees of freedom that we have for tangential field map processing depends on the number of triangles of the mesh. So it can be a million of degrees of freedom. And the question is, do we need all of them? In many modeling scenarios, for example, in this case, the fur design, we only specify some small number of constraints. And we want to create smooth fields satisfying those constraints. This means that there is no need for a million degrees of freedom for the modeling. In this work, we introduce a construction of space of tangential field on complex meshes that one can use to construct subspaces that are appropriate to the task at hand and independent of the mesh resolutions. For tasks like shape modeling or simulations, similar approaches are also used. In this example, we see a complex meshes that is deformed by a few handles only. And in fact, it is only 40-dimensional subspace, while the mesh has several thousands of triangles. In deformations, the difference between one configuration to another is governed by deformation fields. And one might think that we can just simply use the same technique for tangential vector field. But the problem is, deformation fields are not tangential. So new constructions of spaces for tangential fields are needed. Therefore, we propose novel constructions of tangential fields that can be used to construct lower dimensional spaces of tangential fields on highly resolved meshes. And this can be used to create appropriate spaces for tangential field design and processing tasks. Now, let us give a overview of our approach. Our approach consists of three simple steps. First, we do sampling. We throw samples on the surface, and the number of samples corresponds to the desired degree of freedom that one wants to work with. In our constructions, we are using the farthest point sampling for equidistant distribution of samples. Second step is to create region. On every sample, we create a geodesic disk of a predefined radius centered at the sample, and the radius is chosen such that the disk overlaps with the neighboring disks. The last step is to compute the smoothest field on each region. Sampling, create region, and creating the local fields. So, how to construct the smoothest field in the region? let us first look at the constructions of an individual field on the surface. So once we have the region, we want this field to be localized and smooth. So we specify a region of support for the vector field, and we want to construct the smoothest field that vanishes outside of the region. And by the smoothest field, we mean the field that has the least Dirichlet energy. How to get that? For each edge of the mesh, the energy sums the squared length of the difference of the two vectors on the triangles adjacent to the edge. And to measure the difference, one vector needs to be parallelly transported to the other triangle. And to construct a field in the region, we compute a minimizer of the Dirichlet energy of all fields that vanish outside of the region and have unit L2 norm. And this yields to an eigenvalue problems involving the Laplace operator. And one thing that we need to note here is that the eigenvalue problem is only defined on the region. And the region is small, and we don't need to solve in the whole surface. And the minimizer of this problem is not unique, but the lowest eigenspace is two-dimensional. The two eigenfields differ by 90-degree rotations of each vector on its tangent plane. And that's it. That's already our algorithm. So we sample, then we create a region, and we compute the smoothest field in the region. And that seemingly straightforward approach turns out to have remarkable properties. First, the approach is general, meaning it's applicable to all range of tangential fields and discretizations. Only a Laplacian needs to be available. In the paper, we demonstrate three different fields: the vector field, n-RoSy field, and tensor fields. And the second property of the approach is the scalability. We can build large subspaces of thousands of dimensions on highly resolved meshes with millions of triangles. And here is one example of spaces of different dimensions, ranging from 500 to 2000 to 20,000, constructed on the same mesh. And we can see on the right that the storage required to represent bases remains constant. And the reason is that if we increase the dimensions of the space, we need more sample points. Then, as we have more sample points, we can decrease the size of the disks. And because the number of triangles contained in the disk corresponds to the non-zero entries in the basis, we can keep the same non-zero entries for varying subspaces by changing the radius of the disk. Also, the computation time needed to compute the basis remains similar, because even though more eigenvalue problems need to be solved for a large number of subspaces, but each of the eigenvalue problem is smaller in the size compared to the others. And the third property is smoothness. By constructions, the resulting fields of the approach are smooth, measured by the Dirichlet energy corresponds to Laplace operator used. Fourth, we observe that the subspace provides very good approximations of the smooth fields. In this example, we see a blue reference field and red fields that are the projections of the reference field to the subspace. And we can clearly see that they match very well, and the relative approximations error is only 2%. The fifth property is adaptivity. It is very simple to make this method adaptive? What we need to do is to change the metric that we use for sampling and region growing. So suppose that we are interested in designing tangential fields at the face of the model. So we can adjust the metric to get more degree of freedoms on the region simply by scaling up the distance metrics at the area of interest. And by doing so, instead of this uniform sampling, we will get more degrees of freedom in the desired area. And as a result, we could improve the accuracy of tangential field design significantly. And from this image, from these two images, we can observe that the approximated green fields constructed from adaptive sampling line nicely with the reference blue fields. While on the other hand, the red fields that are generated from uniform samplings performs not as good as the adaptive sampling. And we now highlight some cool applications that, thanks to the proposed scheme, can run at interactive rate even for large mesh models. So let us mention that in our setting, we consider an optimization problem with quadratic objectives that often arise in the tangential field design and processing. And the main goal of the subspace constructions is to enable subspace methods for tangential field design and processing. And what we mean by that is, loosely speaking, is to transform an n by n problem to a d by d problem, right? In which n is associated to the mesh resolutions, or it could be the number of triangles or the number of vertices depending on the discretization, while d is the dimensionality of the subspace, and d is chosen to be much smaller compared to n. And by doing so, we can then transform the problems into a much lower dimensionality that we can solve independent of the mesh resolutions, and also much more efficiently. Alright, so the first application that we want to highlight is the vector fields design. And one typical goal of vector field design is to compute a tangential field that are on the one hand smooth, and on the other hand line with input data provided by the user, for example in terms of the strokes. And we implemented a vector field manipulation tool for design that we can use to speed up the design process. If we compare to the reference space, it takes around 50 seconds to solve one user constraint. In contrast, our method allows us to solve it in less than 50 milliseconds. That's 2 orders of magnitude faster. Another applications that we consider is for n-field design. The n-field design can be used to control the stroke directions of synthesized line art drawing. The fields are first aligned to the maximum principal curvature directions of the surface, and then the user can use interpolation constraints to modify the two fields. And the third application that we want to mention is the tensor field smoothing. We implemented a tensor field smoothing tool that minimizes a weighted sum of functions that penalize the deviation from the approximated input field on the left, and harmonic and biharmonic energies for tensor fields as a regularizer to the smoothness. And since the computations in the subspace is very fast, then we can adjust the weight of those two terms interactively to obtain the desired outcome. And you are welcome to read our paper for more applications. And to justify our constructions, we compare our approach to other possible constructions and also to existing techniques. First, let us compare two alternatives of possible constructions. And instead of taking two smallest eigenfields, that what we do here, constrained to the local regions, there are also some other possible choices for local field spaces. The first one is by getting the smoothest field as a result of minimizing the biharmonic energy on the region. So what we mean by that, we specify a boundary conditions on the regions, shown as the yellow area here, and we add a hard constraints of a vector with a magnitude of 1 at the center of the disk, which is displayed by the red arrow in this image. And the minimizer of the biharmonic energy that satisfies both constraints are used as the basis fields. And another possible scheme to create the basis is by creating radial basis functions, and then computing the gradient and cogradient of the radial basis functions as the basis fields. The third option is to compute the smoothest global eigenfields of the model. And then we scale the magnitude by the radial basis functions on each of the sample faces. And we use the result as the basis for our locally supported fields. One other possible choice of basis is to take not only 2 but more eigenfields per selected region. So instead of 2, we could take 3, 6, or even 10. But now let's see why our construction is better. So we compare the performance of the alternatives constructions in approximating the eigenvalues of Laplace operator of the corresponding fields. And with the orange straight line here represent the reference eigenvalues, and ours is the dashed green lines. It is clearly visible that our constructions outperforms the other alternatives by large margin. And now we compare our constructions to the existing approach. So one other possible subspace constructions that can approximate the reference field that can approximate the reference fields very well is the eigenbasis. So what they basically do is they solve a general eigenvalue problem of Laplace operator on the whole surface, right? And once they solve it, they use the eigenvectors as the basis for tangential field design and processing. And despite being powerful in approximating the smooth fields, they require to compute and to store dense eigenvectors of large models. And this limits the applications of the eigenbasis. And in contrast, our method is sparse by constructions. And let's see some statistics here. For the same storage budget, we could have much more degrees of freedom compared to the eigenbasis, and it yields to significantly better approximations. And when we want to target same accuracy, our scheme allows for much less storage compared to the eigenbasis. And looking forward, there's still a lot that we can do with tangential fields. In this work, we limit our focus to optimization problems with quadratic objectives. And for more general problems, additional techniques are needed to be developed that allows us to approximate the objective and its gradients at a cost that does not depend on the mesh resolutions. And the subspace approximations can approximate the low and mid frequency very well, but the high frequency are not captured. Another potential is to construct a multi-level solver for tangential fields problems. Our approach can also be extended to include sophisticated boundary conditions for eigenvalue problems that we use for field constructions. So in conclusions, we introduce a construction of subspaces of tangential vector and tensor fields that are scalable, general, adaptive, and can approximate the smooth fields very well. We evaluate and show that these properties indeed hold, and we also discuss applications that we can build on top of the approach. We also demonstrate that the constructions outperforms the alternatives constructions. And with that, we conclude our talk and we thank you for your time.